All right. Oh, yeah. Okay, so last class with new material, and then it's just so whatever is difficult for you, tell me. I already know that, so I'm going to converting. So that's something I want to do again next time. But now let's go ahead and yeah, talk about the last topic. So second derivatives. Of functions with many variables. So it's not that complicated. It's just whenever you want to take second derivative, then you derive a second time. So if you have many variables, then you can choose to derive with respect to one or some other variable. So consider, and with that you will have essentially everything you need to do to know about derivatives. So consider a function of two variables. So let's say it's f of x and y. Yes, I'm going to try to not go too fast, so to allow you to copy everything. So this function, how many partial derivatives can I have with this function? Two. Yes. Two has two partial derivatives. So it can be f of x y dx, which we write like this, simply just with the small x. So it just tells you that, or you could write with the small one to see it's the first argument, but x is fine. And we also have the second one, which is I could take the derivative with respect to y. So I would write it this way. All right, so this is something we've seen 2 classes ago. So how many second order, second partial derivatives can I get, do you think? Yes. So the function has 4 second partial derivative. So again, all you do is you derive with one variable, and then you derive with the same variable or some other variable. You can do what you want. So we could have. Let's just yeah, okay. Let's. Did I write it? What did I write? Yeah, so let me write it completely. So how I would do it is this. So this is some function. So it looks strange. It looks like a fraction, but actually it's just a function from xy to some value. So I can take a derivative a second time. So the way I would write it is the following. So if I want to derive a second time with respect to x, so d, and then this whole object, dx. Right. So I whatever I got there, then I derive it again with x. And I would write it the following way. So d squared f of xy, and then dx squared. And I could also just write it very succinctly. Dxx, I guess. Yeah, this way. And let's do that with the second one too. So with that one, so the derivative with respect to y. So derive it the second time. Y. And that would be equal to d squared f of y dy squared. Again, sometimes people don't put the parentheses there, but I insist on doing it just because essentially it really needs one. So we have two D's. And you would write it fyy. So this is if I derive twice with respect to x, twice with respect to y. But what I could also do is mix things up a bit. So essentially what I could look is how would the first derivative of x change if I change y. Essentially, that's what I'm asking. So how I would do it? Well, it's the same way. I would just derive first with respect to x. So I would write it this way. So cross derivatives. So we started with the x. So let's derive with respect to y. And this would simply be equal to d squared. So see that I still have 1d, so that's 2d's, d squared. And here I have, so normally so I could write dx, dy, or dy, dx. I'm going to write dx, dy. Just to highlight that I started with x first, and then I continue with y, right? And that would be equal to f xy. And then I could do the opposite. So let's start with y1. Then derive it with respect to x. So, and then the only thing that would change is that here the order is changed. And I would get, so d rather than dxy, I get dyx. So now, do you need time to write or to go? There's going to be a lot of things to write, so keep that in mind. Here it is. So does somebody know one or two things about these two objects there from a previous time you learned math or not? All right. So there's well, let's do that simply. So let's look at an example. So let's have f of xy equals to x squared plus xy. Right? So compute the two partial derivatives, f of xy and fyx. I suggest you start with the first derivative, then you can go on to the second derivative. That good? Everybody is on board? So let's start with the partial derivative. I'm just going to prepare my answers, but not write them. And then look at the cross derivatives. So if you will get it, you tell me. You got one? Yeah. For both of them. Good job. Did the other get something similar? No? Okay, let's start with the first partial derivative. So here, if I take a partial derivative with respect to x, I consider y as some number that's fixed, that doesn't change. So what do I get? So here, I derive with respect to x, I get 2x. And then I derive with respect to x, I get y. All right? And then the second partial derivative. So let's derive with respect to y. Here, x doesn't change, it's a constant. So if I derive a constant, the derivative is 0. That's 0. And then I derive with respect to y, so I get x. And then I'm able to compute my second derivatives quite easily. So there really is no secret for this. You need to practice. So compute derivatives, use rules. I'm being nice with you and always giving you some very easy polynomials. So it's probably going to look like that at the exam. So the goal is not to burden you with very complicated derivatives, but just okay, so let's go ahead and the second derivative. So the second derivative is I derive once with x, I take, so that's this one. And then I derive this with y. And what do I get? So this 2x, there's no y in there, so this disappears. And the derivative with respect to y is just 1, right? And then let's do the opposite. So yx, I start with 1, I get, so it's that one. And then let's derive it with respect to x. So I get what? I get 1. So how funny is that? It's funny because if you look at this formulation there, it looks like I'm just multiplying dx dy, and with the rule of multiplication, I can just invert them and get dy dx, right? And then it's uncanny that I get the exact same answer, whatever the path I take. And so it's not uncanny. So this is called Clairaut's theorem. or also Shor's theorem. Or Young's theorem. So yeah, lots of people have worked on this. So yeah, essentially what this says is yeah, given a function, f of x, yeah, the cross derivative are the same. Or in other words, the order of derivation does not matter. So if you had the function of more variables like x, y, z, then it just doesn't matter. You just treat z as some constant. And as long as you derive with respect to the same variable, so df dy, dy or dy dx it's always going to be the same. So essentially what I can write is just this. So this is equal to that, or simply this is equal. All right. So this is a very neat thing that is quite useful and quite interesting. Okay, so and since we have some time, let me show you how this works. So there is no proof in the book, and yeah, on Wikipedia they have like Clairvaux's proofs, Shor's proof, and Young's. They all introduce a bunch of super complicated notation. No way I'm going into that. I want to have something that's intuitive. So let's go ahead and yeah, show you. So now really you shouldn't copy too much. Just appreciate what we're doing, and then yeah, then we use it. All right. So an intuitive. Actually, we're going to prove something more general, and if it's a more general statement, then it's also true in this special case. So, so why am I doing this? Well, because it's again, it comes back to notions that we are already seeing. So it's good for you to remember that. So remember difference quotient. So remember the difference quotient. I'm just going to put this in bracket because that's something that we already know. So we had y equals f of x, and the difference quotient was delta y delta x was equal to f of x plus delta x. Oh yeah, that's getting a bit small. This. All right, now we see something. The difference quotient was this. So delta y delta x. So it's the change in f of x following a change in x. So it was this minus f of x over delta x. All right. So now this is somehow superfluous because we need the y, because we need the second variable, and I don't want to introduce z and other stuff. So let me introduce some other notation. So producing useful notation. So just this part there, f of x plus delta x minus f of x, we're just going to call this. So if this is just to say we define it this way, so we're just going to say it's delta f of x. So then we don't need y. It's like delta y. It's okay, but it's the change in f of x. Makes sense? Right? Okay. So this is with one variable. Yeah. Is the change. Following change in x. Okay, and now imagine we have a function of two variables. So consider. Again, so f of x and y. So now we could have two difference. So I could either change x with delta x, or I could change y with delta y. So I want to have some meaningful way to know what I'm changing, because I can change one or the other. So let's consider the two cases. So I'm going to call this delta, and then I'm going to say it's delta x. So this is going to mean I'm changing x, and then I'm going to have delta y, which is changing y. So this would be f of x plus delta x minus f of x. And then I could be again changing y, delta y. And then I start at the same point, f of xy, but now I'm adding delta y here. Makes sense? So this is the most difficult aspect of it. In math, once you introduce good notation, then some things can become super clear. So now we know what's changing, and then we can just evaluate the differences, and you are going to see we get the same thing. Okay, so how do we do that? So first, the difference. Quotient. So I'm changing x. So if I take my first difference, then all I care about is this. So let me write it. So it's delta f of xy divided by delta x equals this. So this is just the first difference quotient. Same thing as before, it's just I have some y there, but it could just go away and I would be back with the same thing I had. But now what I'm going to do is also change y. And for this, I'm going to evaluate again this first difference quotient with respect to x, but with a different starting point for y. So rather than evaluating it at the value y, I'm going to evaluate it at the value y plus delta y. So this is at y. And then let's evaluate it at x, y plus delta y. So all I do is add some plus delta y there, so that's just a number. So plus delta y. Plus delta y. Plus delta y. And now with this, I can evaluate the second difference quotient. So now I care about not the change in f following a change in x, but the change in x following a change in y. So that's the cross difference. So I'm interested in the difference of the difference. And by the way, in statistics or in econometrics, if you continue, you're going to see this difference in difference. So that's something that's, yeah, that's a useful concept. So second, mixed difference. So all I care about is the change when I change y of what? Of this change here. Delta y. And now let's just compute it. So it's this thing minus this thing divided by delta y. This minus this divided by delta y. And let's just see what we get. So we have delta x. So it's divided by delta x on both fractions. So let's just put delta x at the denominator. And then I have here f of delta x plus delta x, y plus delta y, minus f of x, y plus delta y. And then I have a minus in front. So this is minus. And then minus, this is plus. All right. So this is what I get. And right away, you can see where this is going. So this is a quotient. I could just flip this around. And here I have just the two central terms, minus x, y plus delta y, minus x, y plus delta x, y. But I could flip these two, and I could have done exactly the same. So let's just call this, again, let's just say what this is. So we're going, because this is unwieldy, so let's just say it's the change in x and then y. X and then y, and then delta x, delta y. That would be this expression. And then let's try doing the second, the order, the different order. Change. So we start with delta y. All right. So so at xy, I want the change in f of x following a change in delta y. So it's x plus delta y. And then I vary the same thing, but just at some further value of delta x plus delta x plus delta x. And then I can, oops, and this is the delta y. Yes, and then now let's have the second difference quotient. And now I did with delta x, so let's now with delta y. change would be delta by changing x of this function there divided by delta x. And so that's just this thing minus this thing. So it's this thing minus this thing. Divided by. And then again, I can do the same thing. So let's now put the delta y at the meter. Here I get this, and this is, there's a minus sign in front of that one, and a plus, so minus times minus gives me a plus. This you could write it the same way, so that would be equal to the second difference, but starting with y. And we're basically done, because here what we have demonstrated is something more general than what we wanted to show. Because what is a derivative? The derivative is the limit of the difference quotient when delta x goes to 0. And here we have shown that this is true no matter the size of delta x. It could be 2 or 4 or 0.0001. It's always going to be true that you can take the difference starting with x and then y, or starting with y and then x, and you always get the same thing. You can see that this is the same as this one. So we have shown that. This. For delta x, delta y. Of course, they have to be different from 0, otherwise you cannot divide. So of course, it's true at the limit. So the limit of this thing when delta x and delta y go to 0 is equal to the limit of this thing with delta x and delta y go to 0. And what are these? Well, of course, they are the partial derivatives. Yeah, maybe a better notation could have been delta x, delta y. I don't know what you think. Since it's not, I didn't take this from anywhere, maybe that would be a better notation. Yeah, I'll think about it for next time. Anyways, so it's the same as, of course, this is the exact definition of what the derivative is. All right. So I didn't take too long because the goal is not for you to remember this proof. But just again, that was a pretext to go back to the difference quotient and remind ourselves what are derivatives. At some point, they're just difference. So second derivative are the change in the first derivative. So a change in a change. Yeah, and as you can see, as long as the multiplication is commutative and the addition is associative, then this works. So any question, or I'm guessing no question. I'm guessing you want applications now. So well, I've shown you the application is just that if you take a function, some function, then if you derive first with respect to x, then y, or y then x, then you get the same result. Yes. But yeah, so now we might go back to our economic application. Optimization with two variables under constraint. This is something that you have to do for the homework. And that you have to do all the time as economists, because all the time we have to deal with utility functions, and we need to yeah, so we all the time need to choose between what good one and good two, for instance. And so this is always a maximization under constraint. So let me show you how we can do it. Yeah. Example. Utility under budget constraint. All right, so we already did some of it. It's just that we didn't check for second order conditions. But this way we can, since we have partial derivatives, then we can check for second order conditions. All right, so the utility is x1, x2. Yeah, I'm not going to define what it is. It's just something. And the budget constraint. So I'm going to have P1 x1 plus P2 for some income n. So x1 is consumption. Good one. Then I'm going to make x2. By the way, now this is important. This is a consumption of good 2, and then P1 is the price of good 1, and is price of 2, and N is the income. So if we were more advanced, we would write something like smaller or equal, because we could decide for some weird reason to throw money away. But we know that people are not going to throw money away, so we can just write an equal sign. That makes things simpler. So does that ring a bell? Did you remember doing something like that? Yes? Yes? We did that before? Ah, okay. All right. Perfect. Okay, so for you, so are you the only one? Are you taking 301 too? Ah, okay, nice. All right, so it's going to pass better. I'm very happy now. But how could they possibly do that? You guys didn't see partial derivatives yet. So now you know. Now you can. Okay, so hopefully this is going to go better. So I'm not allowed to show you a full. Anyways, we don't have time. It's the last class. So so yeah, you could do many other things, like something like, have you heard of the word Lagrangian? Wow. So okay. So this class is just so much easier than no. Lagrangian is much more difficult, right? Don't you agree? Well, first time I saw Lagrangian was in grad school, and because I had never done a optimization before, and I was completely shocked. And I looked at the other people around me, and they were like, "Yeah, sure, sure, sure." But but they have already seen it before. But yeah, first time you see Lagrangian is quite shocking in my opinion. But it's a neat. Okay, so let's not use Lagrangian, because in principle we shouldn't use them in this class. So let's have some simpler methods. So method one. So what we could do is substitute x2 in the utility function get and a maximization problem with a single variable. Okay, so how would that work? So since you already know, so what should I do there? What should I use? So this is my utility that I want to maximize. And I have this budget constraint. Yeah, but that's another way of doing it. Now I'm doing it this way. I want to substitute x2. Yeah, so I have x2 there. Yeah, so what I can do is simply express it as function of the rest, and then I'm going to plug it back into the utility. So and then I can just maximize it, and we already know how to do that. All right. So then I can let's just do all the steps to make sure we understand what we're doing. So this would be O2 minus 1. And then x2 divided by p2. Okay. And then we get by the way, I'm not going to prohibit you at the exam from using Lagrangian. If I ask you some problem with multiple variables, then just use whatever is best for you. Maybe I'm going to say use this method or that method, but usually I don't. If I don't ask you, then you're free to use whatever. So then this is right, and okay. So the problem is right, and now I choose x1 of this. All right, so I have x1 that appears here and here, so I'm going to use partial derivatives. We're going to do an example with our favorite utility function, the cup de glace. But here, let's just start with something completely general. Okay, so then I have a single first order condition. Which is simply that the derivative of my utility function with respect to x1 has to be equal to 0 if I want a maximum. Yeah, so I thought it was very difficult when we found like the maxima and minima and everything of function, but since you're already doing stuff like this, then, but maybe I don't want to presume, maybe you're doing it in a different way. So if that's so, then good, it means, so I'm just going to write what we want to do. So it's x1. And so what does that mean when I replace x2 by this? Essentially, that's embodying in my problem the fact that I have two things to worry about. First of all, when I increase my consumption of good one, then I'm happier because I get more good one. But knowing that I'm satisfying my budget constraint, then I'm also going to lose lose some good two, because I have to exchange some good two I had, sell it, and buy some more good one. So this loss of good two is going to be reflected there, right? So I'm not going to write all the arguments, but it's always there. So I'm just going to write. So first of all, it's my first derivative with respect to x1. So let's write it this way. Yeah, no, a better way would be this way. So u1. So u1 is simply the derivative with respect to the first argument of u, right? Plus, now I have some x1 that's entering the function in the second argument. So I have u2. Then, of course, then I had to derive inside it. So here it was just one, the derivative which is x1, but now the derivative here is minus p1 over p2, because I have this in front of x1. And this has to be. Okay, so have you seen stuff like this before? Or is this confusing? It's okay. Okay. Because I could. We're going to do it with a glass later. So if it's confusing. So again, what I did is I take the first derivative with respect to so the first argument, and then times d1 dx1 dx1. which is of course 1. And here it's the derivative of u with respect to the second argument, so this, times the derivative inside, which is so this thing with respect to x1. Right, this is what we did. And this is just minus p1 over p2. And this is equal to 0. So then I can see what we get. So after substitution, we get. So I'm not going to keep these arguments, but they are there. So just not show them. Not there. They're not there. It's just too long to write it. Okay, so this goes on the other side. So we get plus. This. So you want to. And this is, of course, if you remember, this is the marginal utility 1, and this is the marginal utility. Remember that, marginal utilities? Okay, so we found what we were looking for. And then we want to know whether, this is a dilemma for me. Should I or shouldn't I check the second order conditions? They are a bit long. Either I show you the second method or let's go with the second order there. So just this method there. Because we're checking optimization, so let's check second order conditions. Condition rather, there's only one. So yes, let's see. And it is, of course, if I want a maximum, I want d squared u dx1 squared to be positive or negative? Negative. Okay, good. So we're following. So let's do that. Yeah, so this is my, yeah, I should write it this way. This, so, okay. So d squared u x1. So we derive a second time. So we have how many terms? 4 terms, because here we can derive with respect to this first argument, second argument again, and then first argument, second argument again, and this is just a constant. So let's do that. So this is just going to be again, so second derivative of the utility function with respect to the first argument, plus, yeah, I'm going to write them. Otherwise, I'm going to run out. 4 different lines. Okay, so now I derive with respect to the second argument. And then again, I have my minus p1 over p2 there. And now I can derive this part there, u2. With respect to the first argument, I get u21. And then, oops, I should have. And the second argument. So I can, so u22, and then I derive with respect to this thing there. So again, I get times minus. And this should be smaller than 0, hopefully. So is that the case? So you see what we did, right? We so derive this one with respect to its first argument, its second argument, and this one with respect to its first argument, second argument. And again, we get this. So is there something that we just saw a minute ago that can allow us to simplify this? Some property of cross derivatives? Yeah, exactly. So we know U1, 2, 1. Yeah, that's not a great help, but that's a bit of a help. It can help us simplify. So in the end, we get the following. So U1, 1 plus 2. Let's just keep this first one, U1, 2. Yeah, so, and I have a minus there. So I'm going to put this in front. So minus 2, and then plus U22 times, and this, the minus is multiplied by the minus becomes a plus, so I just get this should be equal to 0. But yeah, I'm pretty sure it's not going to fit on my line. So again, I'm going to drop these arguments. It's not that they're not there, but just it takes too much space. So this is, oh, no, not equal 0, it's smaller than 0. So what do we know about this? Is that true? Well, U11, is that positive or negative, you think? This is how much the marginal utility changes as I increase my consumption of the same good over time. Yes. Let me just, if I have, oh yes, so I have the camera there that I should. So if I have some consumption, so this is x1 and this is x1. So what I'm saying is the first derivative is positive, meaning I like consuming my good one, but the marginal utility is getting smaller and smaller. Why? Because I'm enjoying it less and less as I have more of it. So this is why we see that U11, so the second derivative with respect to U1, is negative. It's becoming fatter and fatter. It's never going to, well, it might be, I don't know, if I get so tired of it that I become very miserable because I have too much with one, but usually because assume that it's like this. And then the second good, U22, well, for the same, it's symmetrical, so for the same reason, it's smaller than 0. So again, if I consume too much of it, so more and more I consume, the less I want. But here there's this interesting middle term. So there's a minus in front of it, right? So minus U12 or minus U21. So to be sure, we have maximum. So this has to be positive. And what is this? These are partial derivatives. So it's how much. So yeah, can somebody interpret what this is? What is U12 or U21? So imagine that good one is coffee and good two is sugar. So what does this mean to say that the cross derivatives are positive? Say something, say something. Yes, almost. So yeah. So example. So if good one is coffee, sugar, then you want two small the more coffee and the more I enjoy an extra amount of sugar, right? So it's not the more I, so it's not the fact that um, I can enjoy more coffee. I'm happier with more coffee. I'm happier with more sugar. The cross derivative is how much an extra quantity of good one affects my enjoyment of an extra quantity of good two, right? It's the, again, if I go back to this proof I showed you there. So it's the impact of the change in the consumption of one good over the impact of the first good. So this is what's happening there. And funnily enough, so if I want to be really sure I have a maximum, then this has to be positive. But so in yeah, in all, what this is that these two terms must be greater than if for whatever reason I they're not sort of complement but rather substitute, then these two terms must be big enough that they counteract the impact of that term. And so just to have some interpretation of what it would mean, why we might not have a maximum. So this is more of a more something that you have to think more about. But what would that mean for this to be not positive but negative? It would be something like I don't know, something that the more you have of one, the more you hate of the other. So what example did I give? So, okay, so going to La Ronde and drinking beer and milk, okay? So if you drink beer or you drink milk, then you're happy. If you go to La Ronde, you're happy. But if you do both and then you take the big rides, then you throw up and you're very, very sad. Okay, so this is what it would mean to have U12 being smaller than 0. So more of one means you enjoy less and less consuming the other. And in that case, then could we get a maximum? Could we get an interior solution where we have both consumption of good one and good two? Well, maybe not. Maybe in that case, I'm better off just consuming milk or just going to La Ronde, but not mixing both. So it means that if I want to maximize my utility, then in that case, I would be better off choosing just one or just the other. But this condition there is to make sure that I have some nice solutions where I have both good one and good two. All right. So that's a lot of words to essentially say that math allows us to learn a lot about economics because we look at what the assumptions that we make in math mean for the result that we get for our economic model, and sometimes it makes us think about what we're saying, especially. So just before leaving, I'm not going to show you the other way of doing it. Just a small example. So copy glass. And well, yeah, we can start it, and then you can finish on your own. So you I don't know what's the letter that you use, alpha. Let's go to the 1 minus alpha. And we still have, yeah, the rest is the same. Okay, so first derivatives. So I think we've already did that before. So is equal to then is equal to 1 minus alpha. And then let's look at the second derivatives. So u11 is equal to alpha minus 1 is minus 2. So is this positive or negative? Oh yeah, I didn't tell you, by the way. This is important. Alpha is between 0 and 1. Okay, so is this positive or negative? All right, right. First of all, is this positive or negative? Positive. Is this positive or negative? Positive. Now that one. Remember, I can only consume positive amounts of good 1 and good 2. Yes, negative. Why? Because here alpha minus 1 is smaller than 0. So that works. And then let's look at the second cross derivative. So second, not cross derivative. So let's derive with respect to x2. So we get minus alpha minus 1. Then is this positive or negative? Negative, yes. Alpha is positive, and 1 minus alpha is between 0 and 1 because alpha is between 0 and 1. So we're good. And now let's look at the partial cross derivative. So let's take that one. Is equal to is this positive or negative? Yes. So we're in good territory because that's what we needed, right? U11 negative, U22 negative, and U12 positive, right? Negative, negative, positive. And then we can just confirm that we really have we have the same thing. So rather than start with 1 and then 2, let's start with 2 and then 1. So now I derive with respect to x1. I get alpha 1 minus. And then Magi is the same thing. And it's also returning new. So now you could just substitute them and find a solution. But so essentially, we have solved the problem for any sort of smooth utility function of two variables. So if it works for any variable, then it works for a single variable, as long as these properties work. So that's about it for today. I didn't have time to start revision. So next time I've posted the exam of last year. So I invite you to try and do it for yourselves. Maybe I'll do that next week. How about that? Because it's, yeah, just to give you some time to do it. I tell you, if you have hard time, last year they had they had a hard time too. So I'm going to make it easier this year. But still, it's good practice. Yeah, I mean, this week we have, of course, Thursday class, but then yeah, next week we only have Tuesday and Thursday. All right. So yeah, okay, I'll do that. So Thursday. Next. Solutions for the So try to do it, because if you just watch me do it without trying, it's not as efficient, of course. All right, so thanks a lot.